Hello everybody, my name is Jeremy Zaro of Team AM Bats, and I'm going to present our project on advanced modular battery systems. To start with an overview of our technical directors, Daniel Wirtz, a senior systems engineer at EaglePicher, and Dan Norick, a senior electrical engineer also at EaglePicher. And a team composition, Adam Bouchard, an electrical engineer, Alexis Charpentier, an electrical engineer, Nicholas Clavet, a computer engineer, Daniel Mark Jr., a computer engineer, and myself, Jeremy Zaro, an electrical engineer. To give a company overview of EaglePicher, it specializes in providing mission-critical solutions to very demanding applications that expose batteries to extremes in temperature, vibrations, power delivery, and service life. These batteries find their way into military, space, and medical applications. EaglePicher has an incredible timeline of accomplishments, from powering U.S. Navy torpedoes in the 1940s to powering the safe return of Apollo 13 astronauts. Some of EaglePicher's batteries are on their way to Mars as you view this. Before we started working on our physical battery management system, we had to do some research and understand important definitions, such as state of charge, the current amount of usable charge at any given point in time on a battery management system. State of health is the measurement of a battery's current maximum capacity relative to its normal capacity based on ideal operating conditions. Analog front end, an electronic component measurement of voltage, temperature, and current, and cell configuration, X cells being in series and Y cells being in parallel. While many aspects of battery design and performance are well understood, there are some persistent topics that plague the ability to accurately predict and track the performance of lithium-ion batteries. Since a battery is a means of storing energy, challenging questions exist, such as how long will a charge last at any point in a cycle's life? How many cycles can a battery survive while enduring temperature extremes? What is the current state of health of a battery or its individual cells? EaglePicher came to URI's ELECOMP Capstone program in search of students to begin to find new approaches to design and reliability model to answer these questions. I am now going to pass this over to my partner, Nicholas.
Team AM Bats has been pushing to design a system which allows us to collect data such as battery cell voltages, battery cell temperatures, and battery current draw. Using this data, we explore new algorithms to produce estimations for the battery's state of charge, state of health, and to model cell resistance growth. Providing such data will help establish a framework for the next generation of EaglePicher technologies, batteries, and systems. The cells in a battery are never perfectly alike. This causes some cells to develop higher internal impedances over time, lowering or raising their capacities faster. The ability to detect and target damaging cells before the entire battery is limited to an individual cell's performance will provide massive benefits in the next generation of high-performance battery systems from EaglePicher. This semester, the team has worked vigorously to develop a BMS system equipped with highly accurate data collection hardware to be able to control discharging, charging, and monitoring of our 12-cell batteries. A resistive load was built to provide a reliable way of discharging our batteries at a high rate. Analog devices provided a development board to measure individual battery cell voltages, a transcoder to convert isolated SPI signal to a regular SPI signal, and a modified Arduino Uno, called a Linduino, to be the microprocessor of our BMS. High-accuracy thermistors were placed on each of the 12 cells and multiplexed to 2 inputs on the Linduino to provide each cell's temperature at any given time. A solid-state relay driven by an output pin on the Linduino was used to switch our load on and off. The BMS created provides the framework for future data collection and analysis to target algorithm development. My name is Nicholas Clavet, a computer engineer, and here are my personal technical accomplishments. In order to collect data from a battery under loading scenarios, a large power-resistive load was created. This load is made of 7 10-ohm power resistors in parallel. The load is very consistent and durable, and is capable of dissipating 1,575 watts. In the first prototype, we used a simple solid-state relay to switch the load on and off. The future iterations of this prototype will have a driver circuit to throttle the current out of our batteries. Current will be throttled through power MOSFETs driven by an op-amp with current feedback to close the loop. Any discharge profile can be provided to the op-amp's non-inverting input from a function generator, and the current flow will follow. To measure the cells in our batteries, the DC2259A development board from Analog Devices was selected. The board is easy to connect to the microprocessor and easy to program to pull all 12 cell voltages. The LTC6811 IC responsible for pulling the cells states that its theoretical maximum polling frequency is 3.4 kHz. However, once implemented, the maximum frequency we could pull each cell voltage at was 125 Hz. This could have been because of limiting speeds in the transcoder, which converts ISO SPI signal from the cell monitor to an SPI signal to the Arduino. This low polling frequency could cause potential problems in the future, and the hardware used may have to be upgraded or switched to an FPGA controller to allow for concurrent processing to speed up and synchronize cell voltage polling. The current prototype uses internal timer interrupts inside the microprocessor to synchronize cell data collection. An interrupt is triggered when an internal timer in the processor matches a user set compare value in the timer's compare match register. Prescaler values can be used to slow the timer increment rate. Combining prescalers and the compare match value, any frequency interrupt can be achieved. When the interrupt is triggered, the processor immediately jumps to an interrupt service routine, where data can be collected. I'll now introduce you to Daniel Mark Jr., a computer engineer who developed algorithms for quantifying the recovery times of our battery.
This semester, I took charge of beginning to structure our code running on the Arduino to calculate important properties of lithium polymer batteries during point-of-load applications. One of these properties is called battery recovery. Recovery is the measurement of the amount of time a battery takes to increase to a nominal voltage after it is disconnected from a load or after the battery has been discharged. Team AMBATS believe this property could be a useful parameter to eventually reach our goal of estimating accurate state of charge and state of health. A healthier lithium-based cell will recover faster than a weaker cell. If this time can be recorded, we can use this factor to train and model the battery cell's state of health. What we have done here is created a function to measure all of the cell voltages twice in succession and compare how much the value has changed between the two poles. Since the battery voltage is never completely static, we aim to look for when the difference between each pole becomes a small variance on the order of less than a millivolt. When a cell is considered recovered, a timer initialized at the start of the function is compared to the time when the cell recovers. This data of recovery time is an output for each cell to the Arduino when the algorithm is complete. A goal for the next semester would be refining the code to be as accurate as possible. This may include grabbing more sample points and defining more efficient functions to help the procedure. The more time taken to do extra steps that may not be needed is crucial time lost. Immediately after a load is disconnected or connected, there is a transient response before the load settles. One of the challenges of monitoring recovery time includes being able to accurately monitor that transient response. This goes hand in hand with current sensing, which Adam Bouchard, one of our electrical engineers, will talk about next.
Current sensing is a particularly important part of this project as it essentially provides the basis for accurate state of charge calculation. The measured current provided by the sensor will be used in conjunction with the time passed between measurements to calculate a discrete time integral that represents our state of charge. The way we'll do that is going to be fairly simple. We're using a current sense amplifier with a pre-calculated gain to output a voltage to be read and interpreted by the Arduino as a current. In this block diagram, the current sensing solution is sitting between the battery and the load to monitor current flow directly from the battery and then pass it back to the Arduino. There is also an analog to digital converter that takes the output of the current sense amplifier and converts it to a digital signal to be accepted by one of the Arduino's GPIO pins. As it is right now, we have not chosen an ADC since we can use the onboard Arduino 10-bit ADC. But given that precision is an important part of this project, we will likely choose to use a 16-plus-bit ADC in the future. The particular model we are considering now is the ADS 1271 IWPR, which is a Texas Instruments 24-bit ADC. This is the existing design for the current sense amplifier. We are using a 10 milliohm resistor with a 0.5% tolerance for accuracy. The amplifier we chose was the LTC6101, which we settled on because it's a high-side amplifier that's capable of accepting up to 100 volts on the inputs. The values of our input and output resistor were chosen to be 850 ohms and 10,000 ohms respectively, to set the gain at approximately 11.7. This way our maximum anticipated current of 35 amps will correlate to a 4.096 volt output, or 34 milliamps per bit. which is acceptable for preliminary testing but will be improved upon next semester when we implement an ADC with a higher bit resolution. Another goal for the next semester is to implement a similar current sensing amplifier on the charging side of our BMS. But with that, I'll turn things over to Jeremy, another electrical engineer, to talk about temperature sensing.
To get a temperature reading that can be read by an analog input-output pin on an Arduino, we use a thermistor, which is a temperature-dependent resistor connected to a voltage divider whose output can be interpreted as an analog input for a microprocessor. The output of the voltage divider is read by one of two 8-channel multiplexers that gives out 8 analog inputs in less than a second to one analog pin on an Arduino. We use this method to save space and use less inputs on our Arduino. We work so much with temperature readings to be used later in our final algorithm for determining state of health and state of charge of a battery management system. We also monitor temperature to prevent thermal runaway, which my team member Alexis will talk more about now.
Monitoring cell temperature is an important consideration for the safety of our system. Since we are working with live batteries, it is imperative to ensure that there is no thermal runaway while we are performing our tests. One method is to create a circuit which will effectively cut off the charging scheme to prevent overheating. We designed a circuit using a comparator, which is an op-amp that compares the voltage output read from the thermistor to a reference voltage chosen based on the maximum temperature that we will allow the cells to reach, and cross-referencing that with the datasheet of the thermistor. When the temperature reaches that threshold, the comparator will then output a matched voltage and redirect the supply of the charging circuit to ground through a MOSFET. To achieve our anticipated best outcome, we need to monitor temperature, cell voltage, and current. In order to collect data, we first had to select our sensing and data collecting components. Since our chosen battery management system uses the Arduino IDE software, we modeled our sensing and data collecting structures using an Arduino Uno, and therefore had to select components which would communicate well with this microprocessor. Using a data logging shield, we will be able to log, graph, and analyze these values in real time to improve our understanding of the cell's functionality. The data collection program we designed defines the necessary components to communicate with the battery management system, SD card, and real-time clock. A comma-separated value file is created on the SD card for each value set. Then the temperatures and voltages of each cell are recorded to the respective files with a timestamp. Using serial values, we are able to see a real-time graph of the values as well. Next semester, we hope to integrate current sensing values to this module and be able to analyze the data we have logged. We hope to develop an algorithm that is able to analyze and quantify the state of charge, state of health, recovery time, and resistance growth of the cells. In addition, to improve the efficiency and operation of our system, we will condense our circuitry to a PCB and design a cooling apparatus for the power transistors. Our end goal is to model state of charge and state of health as a function of parameters such as temperature, recovery time, cell voltage, and internal resistance. We would like to give a special thanks to the following people for their continuous support of Team AMBATS this semester. Our technical director from the sponsoring company EaglePicher, Daniel Wirtz, Brendan Smerbach, our consulting director, and Dr. Harish Sunak, the ELECOMP Capstone Director. We appreciate their guidance and patience this semester and look forward to working alongside them in the coming months.